Hello everyone, welcome back to our class. Let's continuously study Chapter 9, Convection. Section 3, External Flow. In this section, we will study how to calculate the heat transfer flow rate for different flow situations. For example, external flow. The empiric method, generally we have several very typical equations. Always Nusselt number, always relation to Reynolds number and Planck number. For convection mass transfer, the Schroeder number always related to Reynolds number and Schmidt number. So we easily obtain several typical equations. The shape is similar, the modes is similar. C is constant. M, N also is constant. Most of the case we use the empiric equation to calculate the heat transfer flow rate. C, M, N we obtained by the experiment. Here we note T temperature, we use the film temperature or mean temperature. Ts and T infinite average. We use Tf to calculate the Planck number, sometimes Reynolds number. For natural convection, Gr is Grashof number. Okay, here is the general equations. Firstly, for external flow. If the external flow is terminal flow over an isothermal plate, the plate, the temperature is uniform, is constant, uniform. We can solve the boundary equation to get similarity solution. Generally, we understand laminar flow, the Reynolds number most case is smaller than 5 times 10 power fifth. So this number is very big. Is very big. Smaller than this number is laminar flow. For external plate, if the plate the temperature is constant, is same, we think the plate is isothermal plate. In this case, we easily obtain the solution when the velocity boundary layer thickness that E equals 5x over root Reynolds number x. Here is velocity boundary layer thickness. We can use this equation to do some simulate. The second, the local Nusselt number is Nux equals hx times x over k equals 0.332 Reynolds number power half and Planck number power 1 over 3. This equation is very famous. The conditions, another condition is Planck number is larger than 0.6. The third, the ratio of the velocity to thermal boundary layer thickness is delta over delta T is similar to Planck number power 1 over 3. This equation we can do some calculate, do something to obtain the delta or delta T. The fourth, the average heat transfer coefficient. We use this equation to do some calculation to obtain average or local coefficient. For example, the average coefficient is hx average equals 1 over x. hx dx integrate from 1 to x just is 2 times hx. We can use this equation to do some average. The fifth, the mass transfer similar solution. Next chapter, we will discuss the mass transfer. From that chapter, we easily understand the mass transfer is similar to heat transfer. So we can do similar discussion. For example, show the number x average is 0.664 Reynolds number power half. Schmidt number is power 1 over 3. When Schmidt number larger than 0.6, here is mass transfer similar solution. If the plate is still isothermal plate, the temperature is constant. For turbulent flow, the heat transfer is still use a very similar empirical equation to calculate. For example, Nusselt number x equals 0.0296 Reynolds number power 4 over 5. Prandtl number power 1 over 3. The Prandtl number in this range 0.6 to 60, very big range. In this case, the Reynolds number is larger than 5 times 10 power 5th, smaller than 10 power 7th. So the range is still very big. The thickness of the boundary layer dirt is 0.36 x times Reynolds number power minus 1 over 5. Here is the heat transfer. Mass transfer similar. The equation is similar, but the shoved number x equals 0.0296 Reynolds number power 4 over 5 and Schmidt number power 1 over 3. The mode, the equation formation is similar. If the flat plate with constant heat flux, for laminar flow, the Nusselt number equals 0.456 Reynolds number power 1 over 2. Prandtl number power 1 over 3. Here is the Nusselt number. We can use this equation to calculate the Nusselt number. For Prandtl number larger than 0.66. For turbulent flow, we can use similar the formation equation to calculate. For example, Nusselt number x equals 0.0308 Nusselt number power 4 over 5. Prandtl number 1 over 3. The Prandtl number, the range is still from 0.6 to 60. Nusselt number is 36% and 4% larger than the constant surface temperature result for laminar flow and turbulent flow, respectively. Just different. There is some different flow by the isothermal plate, and constant heat flux plate is different, a little different. Okay, the section 4 we discuss the cylinder in closed flow. For example, here is a cylinder, some working fluid over the cylinder. We can find the flow rate, flow pattern. There is some different with the flat plate. So we can separate this pattern two regions. In the front is favorable pressure gradient. The pressure gradient increase, but this region a adverse pressure gradient decrease. So in this case, we use another Reynolds number to calculate especially for the cylinder tube. Reynolds number D is the diameter, equals rho U infinite D over mu, also equals U infinite D over mu. Mu is still mu. Here RED smaller than 2 times 10 power fifth. It is laminar flow. In this region is laminar flow. About this case, Hilbert gave an empiric relationship as follows to calculate the Lucet number. NUD average equals H average D over K equals C RE D M power M plus power 1 over 3. This equation is Hilbert equation. C and M is constant. They can be obtained from next table. The table is Reynolds number in the region from 0.4 to 4. C is 0.989. It's very close to 1. Range 4 to 50 is 0.911. It's smaller. The Reynolds number from 40 to 4,000 become the C becomes 0.683. In this table, we can check CM for different range of Reynolds number. For example, 4,000 to 40,000 different range. We obtain CM is different. We can check the table to calculate C and M. Also, for different shape, the section shape is different. Across the tube is different. For square tube, if we calculate the Reynolds number in different range, we can check from this table to obtain the C and the M. We can calculate different situation, the Reynolds number, from this Reynolds number to calculate the Lucet number. When we obtain the Lucet number, we can calculate the coefficient, heat transfer coefficient. Finally, we can use the Newton's cooling law to calculate the heat flow rate Q. Thank you.